So according to the definition of the physics, we say that the physics is said to be the fundamental study of the laws of nature. And we say that these laws of nature are expressed in terms of the mathematical expressions. So what are the components of these mathematical expressions? And we discussed that these mathematical expressions and that describes about the laws of nature consist with what we call the physical quantities. And we discussed much about the physical quantities being classified in terms of the fundamental physical quantities and also the derived physical quantities. And we further classify the physical quantities in terms of the scalar as well as the vector quantities. So we said the scalar physical quantity, this one is the one that is only being expressed. Actually, these are the quantities that actually has got the only magnitude, and the likes of the mass, time, distance, and different the different examples of the scalar physical quantities. And we also have the vector physical quantities, the ones that has got the magnitude as well as the direction. And further, we discussed about the dimensions of the physical quantities that has been defined as the measure of the physical quantities. And we discussed about the measure of the fundamental physical quantities and also the derived physical quantities. So now I'd like to extend our discussions by looking at the dimensional analysis. Now this is the process of identifying or the verifying whether the mathematical expression or whether the formula is dimensional consistent or not using the dimensions. So that's the definition of the dimensional analysis. That is the process of verifying whether the formula is dimensional consistent or not using the dimensional analysis. So that's the principle behind the dimensional analysis. So now let's say we have the formula given us. Let's say V is equal to 80 plus. Let's say this is a formula for the motion. We have the final velocity, acceleration, time, and this is the initial velocity. So how can you be able to show whether the formula is dimensional consistent or not? So now first thing, we should have to express each physical quantity in the formula in terms of its dimension. So in this case, the velocity has got the dimension given as length over time. So have it as the length over time. So now these quantities should be expressed in the square brackets, the way we discussed about the dimensions. So in this case, we'll have it as the L over T. So these are the dimensions for the velocity. And how about the acceleration? We have it as the L, so it should be that divided by T squared. That should be divided by, now should be 80 squared, like that. And the times, what is the dimension for time? We have it as the capital letter D. So have it as the D there in plus. Now this is also the part of the velocity. We'll have it as this. So L over T. Now from this step, and for the whole entire way out, we want to have to include these square brackets in the analysis. Hence, we'll just have to eliminate the square brackets. So now this is the same as having L over T, and which is equal to, we'll have to cancel this T and the single T here. We'll have L over T and plus L over T. And let's express this one as the single fraction. So now in this case, we'll have L over T, which is equal to 2L over T. Now in the dimensional analysis, should we have any sort of the dimensionless constant? We actually ignored it. In this case, we'll have it as the L over T is equal to L over T. Now in this case, the formula is said to be the dimensional consistency, because what we have to the right hand side is the same as to the left hand side. So again, whenever we are dealing with the dimensional analysis, we ignore any dimensionless constant. So if we say dimensional constant, it means the constant with no units, that is dimensionless constant. Let's say have v square is equal to u square plus, let's say 2a. So let's say this is the case. So now let us see if the formula is dimensional consistence or not. So what is the principle behind? So we have the final velocity, which is just the velocity. So now for this case, this square is the external power. So as we'll be expressing the velocity in terms of the dimensions, this power will be outside the square brackets, in the sense that we'll have now L, that should be L to the power 2 divided by d to the power 2, that which is equal to L to the power 2 divided by d to the power 2, that which is plus, and this is the constant, we just have to ignore it. And what is the acceleration? We'll have L d to the power 2, like that. And what is the displacement? We'll have it as the length, so in this case we'll have it as this. So this is the same as having it as L over t, both being squared, which is equal to L square over t square, and plus L square over t square. So expressing this one as the single fraction, we can have it as L square over t square, which is equal to 2L square over t square. We just have to ignore the constant. In that case, we'll have L square over t square is equal to L square over t square. Hence, the formula is dimensional, actually a consistence, since what we have there is the same as what we have to the other side. So keep that in mind. And we have the formula, let's say, and we have the formula which says that the mass is equal to the density times the volume. So let us see if the formula is the dimensional consistence or not. So what are the dimensions for mass? We'll have it as, should be the m, which is equal to, how about the density, that which is now been given as, the density is given as the mass of the volume, over volume. In this case we'll have it as mass and over volume, which is, should be L cube, and down there in the terms, what is that of the velocity? We have it as the L cube. So in this case, this and this will cancel, have the m is equal to m. Hence the formula is the dimension, is said to be the dimensional consistence, as you can see. And how about if we have this case, let's say have the displacement is equal to initial velocity times time plus half acceleration t square. How can you be able to show whether the formula is dimensional consistence or not? So what are the dimensions for displacement? We have it as the L. So it should be that which is equal, this is the velocity, we'll have it as the L over t. So we'll have that and as that, and the times t, which is given as that plus, this is the constant, we just have to ignore it, in the sense that we'll have it as the acceleration, that is L over t square. That should be that times t square. So in this case we'll have it as this. So now this one will have to cancel, in the sense that this one also have to cancel. Have it as the L is equal, that should be L plus L, that will be given as the 2L. So ignore the actual constant, in the sense that we have L is equal to L. Hence the formula is said to be the dimensional consistence. So bear that in mind. And sometimes you can also have the formulas that consist with the dimensional constants. So these are the constants that actually that has got the units. And for instance, let's say we have the formula which is given as the force is equal the actually dimensional constant which is given as G times the mass 1 times the mass 2 divided by, let's say, the divided by the radius square. So now, assuming that this is the force, this is the mass 1, this is the mass 2, and this is the radius. So how can you be able to determine the dimensions for the actually the gravitational constant which is given as G, if this is the case using the dimensional analysis? So how can you be able to go over that? So now, first thing, we should have to make G as the Sargent formula. So in this case, we'll have to cross multiply, have it as a G m1 times m2 is equal to f r to the power 2. So in this case, the G will be given as f r to the power 2 divided by mass 1 times the mass 2. Then now we should have to express these quantities in terms of their dimensions. So mind you, we are to use the dimension analysis. So what is the dimension for actually a force? We have it as the kg. So by the way, the unit for force is given as the formula for the force is given as the mass times actual acceleration. So which means the dimensions for force will have it as the m times, what about for the acceleration? We have it as now L divided by the d square. So have it as divided by a d square. And how about that of r square? So radius corresponds to the length. So which means we'll have it as the times length and at the power 2 and that divided by the mass 1 times mass 2. All these are the masses with the similar actually a dimension. So have it as actually m square in that case. So it is just a matter of using the concept of the algebra to have to express that one. So in this case, this is the same as mass in the times. So in this case, we'll have it as the L cube and that divided by d square, and of which the overall divided by m to the power 2 should be like that. So mind you, we are having the dimensions for G. So in this case, it means we'll have it as this. So by the way, G will be given as, now have m L cube divided by d square and the times 1 over m actually square. So in this case, we'll have m and this m will be cancelled, in the sense that we'll have L cube divided by now m d square. So these are the dimensions and for the gravitational constant, Newton's gravitational constant, which is given as actually G. And at your own time, try to deduce the units for actually this gravitational constant, in that case, using these dimensions. So try to have that out at your own time. So that's how the dimensional analysis can be used to determine the dimensions for the actually dimensional constants. And also think about this one as well. Let's say we have the formula for kinetic energy given as K is equal to rho Ksp, which is given as the momentum divided by, let's say, 2m. Let's say the kinetic energy is having the units given as, let's say, kg meter square over, let's say, second square. So now this is the mass, by the way. Using the dimensional analysis, try to deduce the dimensions for the momentum and the units, if that's the case. So try to have that done at your own times. And now let's say we have this case. Let's say have the formula given us. Let's say period given as t is equal 2 pi times the square of, let's say, the mass divided by, let's say, a k. Now, where k is the dimension constant. So how can you be able to deduce the dimensions for actually k if that's the case? So try to have that an out at your own time to deduce the dimensions of that particular constant k. Now, sometimes you can have, let's say, the formula which is dimensional consistent, and be able to have, let's say, the exponent that is making the formula to be dimensional consistent. For instance, now we have, let's say, the formula for acceleration is equal to, let's say, 2x and that times the term to the power p. Let's say the formula is said to be the dimensional consistency. So how can you be able to have the power of the exponent p if this is the case? Now you are sure that the formula is dimensional consistency. So let's have to express each and every quantity in terms of each dimension. We go for acceleration, that is giving us the now L over t to the power 2. It can be that. And of course, using the laws of indices, you can be able to express this one in other ways. We'll be able to discuss that one. Now this is the constant to have to leave it out. And this is the displacement, that is the length. So have it as the L. The times, this is actually the time which is given as t. So have time, and this is the external exponent which is p, or have it as the, in that case. So now using the laws of indices, now this is the same as having it as, of course, we'll have it as the L over t to the power 2, which is equal to L to the power, actually L t to the power p. Laws of indices will have it as the L times t to the power negative 2, which is equal to L t to the power p. That's why you can have it there. So now you can see that L to the power 1 is equal to L to the power 1. If we tend to equate actually the dimensions in the correspondence. And how about we'll have t to the power negative 2 is equal to t to the power actually p. In this case, since the bases are the same, it means the powers also being the same. So which means the p will be given as negative 2. That is the value of p that is making the formula to be dimensional consistency. Now how about if we have this case? Let's say we have this kind of a case. Now should be ready to say we have the formula for the velocity which is given as v squared is equal to, let's say, 2a x to the power, let's say, m. So what is the value of, let's say, the exponent m, which is making the formula to be dimensional consistency? So just have to ensure that you are much familiarize yourselves with the laws of indices, because are the ones that we literally use in the analysis itself. So this is the velocity that will be given as the L to the power 2 divided by t to the power 2, which is equal to, this is the dimensional constant. So dimensional is constant, we just have to read it out. So have the acceleration that is given as L divided by t to the power 2 should be that times. Now this is the displacement that we can have it as the L to the power actually m. So that is, now this is the same as L to the power 2 to the power 2, which is equal to L over t to the power 2 times L to the power actually m. Now we have the expressions with the same basis. So mind you, this is, that one is having the power of 1 there. So in this case, this is the same as having it as L to the power 2 times t to the power negative 2, which is equal to, now t to the power negative 2 times L to the power 1 plus m, according to the laws of indices. So now just have to equate the dimensions, and accordingly, in this case we'll have L to the power 2. Now in this case, L to the power 2, it is the same as L to the power 1 plus m. Now since the bases are the same, it means the powers will be the same. In this case we'll have 2 is equal now 1 plus m. Now in this case the m will be given as 1. So that is the value of the exponent m, and making the function to be actually making the formula to be dimensional consistence. So keep that in mind. Let's try to go through the following problems and see. And what if we have, in this case, let's say have, now should be, let's say we have the formula. A term is given as, let's say h to the power p times the square of 2 over, let's say, g. So now, what is the value of the constant, let's say, exponent p, that is making the function, that is making the formula to be dimensional consistence rather. This is the term, this is the height, let's say this is the acceleration due to the gravity. How should we be able to go over that one? Now here are the principles. So now first thing we can also think of, now we should have this case. What is the dimension for, let's say, g? We'll have it as in this case. And how about the height? That is the length. We'll have it as the L to the power p. The times. Now in this case, this is the same as, now in this case, that one is the constant which is given as, now should be a 2. We just have to leave it out. Now this is the same as having it as, now we'll have it as the 1 over. Now for this case, let me just have to highlight this one first. Let me just have to express this one first for easy understanding for this case. Acceleration due to the gravity is the same as the acceleration, with the dimensions given as L divided by d to the power negative 2, and of which this is the same as having it as, now should be a positive 2 rather, now which is the same as L times d to the power negative 2. So that is, so now which means we'll have a t, the dimension for the period, which is the time, and the L to the power p times, now we'll have the dimension for the acceleration due to the gravity, that will now be given as this. Now since we ignored the actual 2, it means we have it as this. We have 1 over, now should be given as this, 1 over, now should be L g to the power negative 2 will be given as that, in outside to the power half. We can have that and as that, and of which this is the same as the period is equal L to the power p and the times. So now we'll have to ignore the angle brackets, actually the square brackets by the way. So which means we'll have it as, now we'll have it as, now L to the power negative 1 times t to the power positive 2 in the overall to the power half, and of which this is the same as the period is equal to L to the power p times, now have L to the power negative half and times t to the power, now should be 1. According to the laws of indices, if you have a times b to the power m, this is the same as a times actually a to the power m and b to the power m. That is the essence behind that. So now we'll have this one as this. So now we'll have t is equal to, now we'll have L to the power p minus half, because the bases are the same here. We just have to add the powers. And now times are actually t to the power. So now keep that in mind. So now as you can see that we have this one's t to the power 1 and also this one t to the power 1. So now what is lacking is now something to do with the L. How should we be able to have that one out? So you should have to understand about this one, according to the laws of indices as well. having t, it is the same as t times 1, which is equal to L to the power p minus half times t to the power 1. And having a 1 there, it is the same as having as t times L to the power 0 is equal to now L to the power p minus half times t to the power 1. So in this case, we'll have to equate the two. So since the bases are the same, it means we'll have to equate the powers in the sense that we'll have p minus half is equal to 0. So which means the p will be given as the positive half. So that is the value of the exponent, making the function to be the dimensional, actually, consistence. So keep that in mind if that's the case. And how about if, let's say, we have this case? Let's say we have this case. Let's say acceleration is equal to a k times r to the power n. Let's say v to the power, let's say n. So what are the values of n as well as the m, making the formula to be dimensional consistence? Let's say k is the dimensionless constant. So try to have that one out at your own time and see how best you can be able to have that case. And let's say we also have the problem. Let's say the displacement x is said to be a k times acceleration to the power n, and let's say times t to the power, let's say n. Find the values of the powers, making the equation to be dimensional consistence. So try to have that one out, assuming that the k is dimensionless constant. So thank you for your time in the watch. So try to go through my examples to be able to mastermind the dimensional analysis concept. Thank you.